Our second objective on our practice test B were to draw simple Bohr models of isotopes. The word Bohr is named after a scientist, a chemist, Niels Bohr, who developed our solar system model. So this is just in his honor naming those Bohr models of isotopes. You could also just say simple models of isotopes. We're going to be asked to write the standard notation and calculate the average atomic mass for an element given the isotope data. Let's read together the little paragraph about sulfur. Sulfur has 4 natural isotopes. Isotopes, that's a good word to remember. Isotopes are atoms of the same element that differ by the number of neutrons. Isotopes are atoms of the same element that simply differ by the number of neutrons. Same protons, same electrons, but they're going to weigh a little different because of the neutron number. And remember, neutrons does not affect the chemistry of an atom, so therefore they all have the same activity, they're just weighing a little different. Sulfur has 4 of these natural isotopes. The first isotope with a mass of 31.972 and a relative abundance of 95.002, by far the most abundant isotope. Now when I hear that, I know that I'm going to be asked to write standard notation, so I'm just going to take a moment and turn that first sentence of data into a standard symbol for all isotopes. I find it easiest to write the standard notation first and then draw the model. Then we can use our math right there from the standard notation. So we're knowing that it's sulfur. We should look up sulfur and know that it's number 16. The weights will vary, but its atomic number is constant. It's identifying as sulfur. Sulfur is number 16. So all the way across, I can get that ready for all 4 isotopes. That's a constant. What will differ is how heavy it is. So if the first isotope has a mass of 31.972, let's round that to the nearest whole number for its standard notation, 32/16. The second isotope with a mass of 32.971, let's round that to the nearest whole number, 33/16 for the second standard notation. And the third isotope with a mass of 33.967, that would give us a mass of 34/16. And the fourth isotope with a mass of 35.967, that gives us a nearest whole number of 36 AMUs, atomic mass units. So the first thing I would do as I read through this paragraph is pull out the standard notation. The standard notation grid then can help me draw simple models of the Bohr atom. To draw the simple model, I'm going to just draw a circle to represent the nucleus. And that circle will be a constant throughout. All the atoms will have a nucleus. When we identified sulfur to have 16 as its atomic number, it told us clearly that it would have 16 positive protons. If it didn't, it would no longer be sulfur. 16 positive protons. The other part we can do is the number of neutrons. Isotopes will vary by the number of neutrons, so each time we're simply subtracting from each isotope. 32 minus 16 gives us 16 neutrons in the first isotope. 33 minus 16 gives us 17 neutrons in the second isotope. Same pattern, 34 minus 16 would give us 18 in the third drawing. And 36 minus 16 gives us 20 neutrons in that last isotope. The sum of the two parts gives us the mass number down below as we recorded. Protons are the same, neutrons will vary. The last thing we need to do is draw for 16 electrons. Let your periodic table guide you. Sulfur is in group 6A, 6 valence electrons, 6 electrons in the outermost shell. It's in period 3, so I'll know I'll draw 3 energy levels. Energy level 1 energy level 2, energy level 3, period 3. Is a constant throughout each of those pictures, so I get those energy levels ready. 2 is the max in the first shell, 8 more in the second, giving us the 6 we need to achieve 16 electrons, 2, 8, and 6, all the way through. 2 in the first, 8 more in the second, 6 in the third energy level, a total of 16 electrons, 2, 8, 6, 2, 8, 6. And again, those little E's can be placed in there to represent the negatively charged electron particles. Atoms of the same element that are identical in every way except the number of neutrons are known as isotopes. The last thing we'll do is to average the weights, a math problem, finding the average out of a sample of 100 atoms. So I'm going to be pulling data from up top and setting it up down below. Alrighty. So the first isotope, isotope 1, had a mass of 31.972 atomic mass units. Its relative abundance was 95.002% is parts out of 100 parts. Isotope 1, its mass of 31.972 times its relative abundance. Added to the information from number 2. The second isotope had 32.971 atomic mass units times its relative abundance of 0.76%. Abundance changed into from the decimal into the percent here, so we're going to use divide by 100. The third isotope, 33.967 atomic mass units times its relative abundance of 4.22. Parts out of 100 parts are percentage. And the fourth isotope, its information, 35.967 AMUs times its relative abundance of 0.014 over 100. Averaging the 4 isotopes together is taking each weight and multiplying by its relative abundance and then adding those together. And let's hit that together on our calculator. Pause if you need to, hit it out, and let's reach a common answer. First one, 31.972 times 95.002 over 100. I get 30.374. Second one, 32.971 times 0.76 over 100. I get 0.25.